For decades, it's been one of the greatest dreams of science fiction, right? A ribbon stretching from the Earth all the way to the stars, a literal highway to the heavens. Well, this isn't science fiction anymore. Today, we're going to crack open the engineering blueprint to see how we could actually build one.
So let's just get right to it. The big question, is this really possible? Could we do it? Well, the answer is kind of complicated and honestly pretty surprising, because the entire way we think about tackling a project this massive has completely changed. And this is the real game changer. We're moving away from the idea of some giant, secret, all-or-nothing project. Instead, this whole challenge is being treated as a series of smaller, provable steps, with all the plans laid out in the open for anyone, and I mean anyone, to see and help improve.
But first things first, we have to face the single biggest hurdle, a problem of pure physics that has basically stopped this project in its tracks for 100 years.
It all comes down to this concept called scale height. It sounds complicated, but it's not. Just imagine dangling a steel cable from way up in the sky. At some point, that cable gets so long and so heavy that its own weight just snaps the link at the very top. Well, that maximum length, right before it breaks itself, that's its scale height. So how strong does our material need to be? The blueprint is calling for a scale height of around 136 kilometers. Now, to put that in perspective for you, no conventional material on Earth even comes close. Not even a little bit. This isn't a job for steel. This requires a legitimate supermaterial.
And this chart really just lays it bare. Our best high-strength steel, it tops out at around 1.5 gigapascals. The design for this elevator requires a carbon nanotube composite, or CNT, with a strength of at least 5 gigapascals. It's just in a completely different league, not even the same sport.
But here's what's really fascinating. Even with a miracle material like carbon nanotubes, a uniform straight cable would still be under such immense stress at the top that it would fail. So the engineers came up with this really elegant solution: tapering. The tether is designed to be thickest at its highest point, out in orbit, and then it gradually thins out as it gets closer to Earth. It's a brilliant way to perfectly distribute all that stress along its entire length.
So we've got the super material, but how do you actually weave it into something that can survive in space? Well, you don't just build a simple cable. You build a suit of high-tech, flexible armor, engineered with multiple layers for what is literally the harshest environment we know of.
So the outer layers are all about defense. First, you've got a sacrificial bumper. Think of it like the thin skin on a spacecraft that's designed to take the first hit. Right below that, there's a dispersion veil, which is basically a high-tech felt that spreads out the impact energy. And then a thermal spreader mesh, because you have to manage these brutal temperature swings between direct sunlight and deep shadow.
Then, inside all that armor, you get to the functional core. You have the primary carbon nanotube ribbon that's doing all the heavy lifting. It's all held together by these advanced glues designed specifically for the vacuum of space. And this is so cool, it has an embedded fiber optic nervous system that's constantly reporting on the tether's health, feeling for strain and temperature changes along every single meter.
Okay, so we have the materials and we have the design. But space is actively trying to destroy this thing 24/7. So let's look at the cosmic threats it has to face and the really clever solutions that are built right into the design.
All right, first up, the constant hail of micrometeoroids. Now, don't let the micro part fool you. These are tiny specks of dust and rock, a lot of them smaller than a grain of sand, but they are traveling at speeds over 6 kilometers a second. How do you stop something like that?
Well, you use this absolutely ingenious idea called a Whipple shield. It's a two-stage defense. That outer bumper layer, it doesn't actually stop the projectile. It vaporizes it on impact. It turns a solid bullet into a harmless cloud of gas. Then, the second layer, that dispersion veil, easily catches that cloud. And all the while, the fiber optic sensors are pinpointing the exact location and the force of the impact. It's brilliant.
But it's not just the things you can see that are dangerous. The vacuum itself is a threat. Specifically, something called atomic oxygen.
So in low Earth orbit, the sun's radiation breaks apart normal O2 molecules into these single, highly reactive oxygen atoms. And these atoms, they will essentially rust or just eat away almost anything they touch. The solution? An impossibly thin shield, just 50 nanometers thick, made of a ceramic-like material that these angry little atoms just can't chew through.
Okay, so the science and the design are absolutely incredible. But for me, what makes this project feel truly real is the practical, step-by-step roadmap that they've laid out to actually get there.
You see, they're not trying to build the whole thing at once. It starts small. 10-meter ribbons on a lab bench. Then 100 meters outdoors to test it against the weather. Then a 1-kilometer surrogate to master manufacturing. Each phase de-risks the next one, building confidence and capability until they're finally ready to test a 100-kilometer segment in actual space.
And this is what I mean by practical. They have already developed a detailed 5-step procedure for field repairs. This shows it isn't just some grand vision, it's a project where engineers are already thinking about the tools a technician is going to need to fix it thousands of kilometers up in the air.
But, maybe the most revolutionary part of this entire project isn't the material science or the orbital mechanics, it's the philosophy behind it all.
This single line from the project documentation, it says everything. This isn't a classified military project or some secret corporate venture. The entire blueprint is designed to be open.
Think about that for a second. An open-source moonshot. All the designs, all the code for the sensors, all the test data, it is all being released to the public. They're even committed to publishing their failures because a negative result is just as valuable to the global engineering community as a success. This is how science is supposed to work.
So in the end, this blueprint is about way more than just one project. It's a new model for how we can build the future. If an open, collaborative, step-by-step plan can put a space elevator on the table, what other impossible dreams can we build now?